The max operation returns the maximum value of a tensor along a specified axis. If no axis is specified, it returns the maximum value from the entire tensor. And in the backward mode, this function is defined as the piecewise function. 1 if x is the maximum value and 0 otherwise. In case if we have several maximum values for our tensor or along a specified axis, we need to return 1 per every specified position. So this operation in backward especially a little bit more complicated than it looks at the first glance, but let's try to do our best and make the implementation step by step. Okay, define max function, self as the first, axis as the second, and we can use an optional data type. Inside we use the union between integer or the tuple of bunch of integers. Okay, I hope that this should works fine. And we have one more, keep dimensions as the boolean data type, and we can install by default to false, and we return back the tensor data type. Case 1, it's very simple case, max with no axis. We need to have just the scalar output, and we have this tensor example A1 with 1, 2, 3 and 4 in the data, and when we call max it should be 4 in B2. When we run the backward mode, our gradient expected to be 0, 0, 0, 1, because we return this 4 at the latest position of the vector inside the tensor. And we just need to mark that right over here we have the maximum value right in this position. For the forward mode we can use output, and we call numpy max and self.data as the data for the forward mode, and we put axis just straight to this numpy max because it's absolutely the same API, and keep dimensions as the keep dimensions. All the other steps are pretty similar. Yeah, we just define the dependencies list and return tensor with output self.requires gradient and dependencies list. So for the backward mode we need to define the backward function. Yeah. And again we have similar actions. We need to append to the dependencies list, leave with self, and with the backward as the gradient function. During backpropagation we assign a gradient of 1 to the position of the maximum values by identifying their position, and you can see the expected result in our example. So we can use the mask and find where the self.data intersects or equals to the output. So where the original data the same as the output, where we just compute the maximum value, and then we need to return our mask times the gradient output. Okay, let's run this code and check our example, and it works fine. Yeah, we just return exactly what we expected, 0, 0, 0, 1. Yeah, just only 1 at the position of the maximum value. And case number 2, it's maximum value with duplicate maximums. It means that in case if we have 2 maximum values in our tensor that just duplicate each other or more than 2, we need to assign the average to each of the following position, because in this case we need to split the gradient equally among all the positions where the maximum values assigned. And let's try to check, and right now it's not work, of course, because we just assign 1 to the position of the maximum. So what we need to add? We need to count the numpy.sum how many maximum values we find in our mask. So we just compute how many with this count, and then we multiply mask times the gradient over the count. Okay, let's check how it works. Rerun this tensor, reneed the tensor class. Okay, and it works fine, and previous still works fine, yeah, because we just found only one item at a time, and count equals 1, and if we divide the gradient by 1, result is absolutely the same, yeah, so everything works fine. Case number 3, maximum values along a specific axis, like axis equals 0. In case if we use the specified axis, we need to compute the maximum along the specified axis. And in this case, we need to return 5 and 5 in forward mode for the B3, but when we run the backward mode, we expect that we have 1 and 1, because we need to find the average along the specified axis. And in case if we have just our implementation and run this code, we use the kind of mask that we defined globally for all of the items in our tensor without any axis implementation in our backward mode. It means that we need to check if the axis is none. Without this axis parameter, we just count total max element, yeah. Okay, and mask, yeah, it doesn't matter, yeah, with axis or without, we compute the mask by the same way. But what we need to do if we have the axis, we need to change the logic of count. We need to provide axis and keep dimensions as true, because we compute our mask along the specified axis. We sum up the mask along the specified axis and preserve the dimensionality of the matrix. But that's not everything. We need to expand the gradient. Let's create gradient expanded variable, and we need to run numpy expand dimensions for the gradient along the specified axis, because we cannot be sure that the dimensionality of the gradient satisfies the axis dimensionality of the tensor, yeah. And then we need to return the mask times the gradient expanded over the count, yeah. And I hope in this case we just aggregate the mask along the specified axis, and then we divide the gradient by the right count along the specified axis. Let's run this code and try to check how it works. And you can see that it works fine. We return back the correct tensor with the correct dimensionality and the expected values. The last piece is keep dimensions true. In case if we have keep dimensions true, we need to ensure that the gradient shape aligns within the input tensor during backpropagation. It means that we need to check if keep dimensions. If keep dimensions is true, the output already has the correct shape, so no expansion is needed. We just use the gradient. If keep dimensions false, we are right over here in the branch of else. the output is reduced along the specified axis. So in backward mode, we must expand the gradient to match the original shape for proper broadcasting during multiplication between the mask and gradient expanded. So now let's reinitialize our tensor and run this code. And everything works fine. You can see that we skip dimensions, just return back the redundant dimensionality. Yeah, we add one more dimension above this vector of the gradient vector. Okay, and I hope now it works fine. Let's try keep dimensions with axis 1. Okay, and looks like this works fine too.